Hello everyone, welcome to the lecture series of operating systems. And today we will be going to study about the inter-process communication, in which you are having two models, shared memory model and the message passing model. And also we will be watching about the client-server communication, how two different systems in two different networks can communicate with each other. So for this purpose, we have the concepts like sockets, remote processor calls and pipes. So first, let us see what is an inter-process communication. When two processes want to communicate with each other, the operating system will provide you a mechanism in order to make these two processes wanted to communicate with each other. Okay, so the inter-process communication is a mechanism which is provided by the operating system to make two processes to communicate with each other. Okay, so before going to the inter-process communication, let us see what are the types of process present while executing in CPU. If you see, we can have two types of process. One is independent process and the other is cooperating process. So in case of independent process, the independent process will not share its data to other process, or it will not take the data from other process. So in simpler manner, we can say that the independent process will not be affected by other process, as well as it will not affect the other process. Whereas cooperating process is a process which will share its data to the other process, or this process may take data from other process. So in simpler, this cooperating process can also be defined as it is a process which will be affected by other process, or which can affect other process. So let us see the reasons for this inter-process communication. So first thing is information sharing. It provides an easiest way to share information between multiple users who are logging into your system. Say for example, if you consider a multi-user multitasking operating system, in that case many users will be logging into the system. So here if you consider if you are working with your putty environment, so in that case two users can log in with two different ID and passwords. So when both the users log into the system at the same time, and if they wanted to communicate with each other, or they wanted to transfer files with each other, due to inter-process communication mechanism, this activity will become easy. And then we have is the computation speed up. So if you consider, say for example, you have a code of 1000 lines. So let us assume that our CPU is capable of executing each and every instruction. So for executing one instruction, it may take 1 millisecond. So in that case, in order to execute our 1000 lines of code, our CPU will take 1000 milliseconds. But whereas if there is a process, if there is a inter-process communication, if there is inter-process communication mechanism in your system, then this process can be divided into different parts called threads. Okay, so once a process can be divided into different threads, the total number of instructions. So thread here is a part of your program, a small part, a basic unit of execution. Okay, so that small part of your process, that 1000 lines of code, say for example, it can be divided into 4 threads consisting of for example 250 instructions. So in that case, when you are having multi-core processors, so if your CPU is if your operating system is capable of executing multiple processes at a time, then all these 4 threads can be executed simultaneously. So while executing these 4 threads, you need to provide communication between these 4 threads in order to share their information and get the overall result. So if you observe, to execute these 4 threads, so it needs only 250 milliseconds. If you assume each thread consists of 250 instructions, so in order to execute each thread, it takes 250 milliseconds. So we are considering that all these threads are being executed simultaneously. So if you calculate the overall time within 250 milliseconds, the total process can get executed completely. So instead of waiting for 1000 milliseconds to complete its execution, a process can complete its execution within the smallest time than the actual execution time. So this is also an advantage of using the inter-process communication system. And the third reason for using this inter-process communication system is modularity. So as you try to develop a complex software, such complex software can be easily divided into parts or modules, and these modules can communicate with each other in order to share the information using inter-process communication. And then the last reason is the convenience. So that if you are allowing a user to share his information with others, he can easily communicate with each and every other process. Okay, say for example, if you are trying to write some Word document, so if you are trying to write some text in your Word document, at the same time you may want to listen the music. So in that case, both of these process, Word document as well as your music application, should have communication with each other in order to execute in the CPU. So user feels that both the applications are running simultaneously, whereas in background this process will be communicating with each other and moving in and out in the CPU for execution. So now let us see the types of inter-process communication. We have two models which provide the communication between two processes running in a system. So one is the shared memory model and the other is a message passing model. So now let us see what this shared memory model is. So in shared memory model, so if you observe, the total inter-process communication mechanism will take place only with the cooperating process. We have seen two types of process. So one is independent, other is cooperative. So in independent case, if the process is independent, there is no need of sharing information with other process. The thing only, or this mechanism will comes into action when two cooperating processes are being executed in the CPU. Okay. So in that case, the first model is a shared memory model. So this shared memory model is executed or is done in the cooperating process. So when two cooperating processes are executing and when they want to communicate with each other, in this model, a common region of shared memory will be executed. For example, if process A and process B, if you observe the diagram, the process A and process B are the two cooperating processes which want to communicate with each other. So when they want to communicate with each other, each process will be allocated some amount of memory in the main memory. So in that case, when the process A, if process A wants to communicate, wants to share something with process B, in that case, a common memory segment for both the processes will be allocated. Okay, so if process A wants to communicate with process B, the overall memory allocated for process A, say for example, if process A wanted a memory of, say for example, some 10 MB. So in that 10 MB allocated for process A, some part of memory. So see how whatever the variables or whatever the data the process B is going to share, all those variables and data are placed in the some part of memory segment in process A. So the overall 10 MB allocated for process A, in that some amount of memory is taken and placed as a shared memory segment. Okay, so all the common variables which both the process A and process B are using are placed in this shared memory segment. Now, when the process A executes and provides some information in the shared memory, this shared memory will be accessed by the process B. So, in that case, in this model, the operating system will execute some system calls in order to establish a shared memory segment. Okay. In general, operating system will not allow two processes to communicate to share the same memory segment. Okay. When both the process try to modify the contents of the memory, there may be a conflict in the output result. So for that case, in general, the operating system will not allow your processes to share the same memory segment. For that purpose, in order to allow these two processes, now our process A and process B, to share a common memory segment, the operating system will execute some system calls so that this shared memory segment will be established. So once a shared memory segment is established, then your kernel or operating system will not take an active part in the communication. Then this shared memory region, where this shared memory region is present. So this will be present in one of the memory allocated for one of the process. So process A will have some memory in your main memory, as well as process B also will be allocated some main memory some memory in your main memory. So in that case, either some part of process A's memory or some part of process B's memory may be allocated as a shared memory segment. Okay. So the other process which wish to communicate with the process, suppose if process A has a memory in main memory and the process A's memory part of memory is allocated as memory segment, shared memory segment, then in that case, the process B, if it wants to communicate, so along with process B's address space, it also attaches the shared memory segment's address location with the process B, so that the process B can access all the elements present in its memory as well as the shared memory segment. Okay, so the only drawback in this shared memory model is it suffers from cache coherency issues. As we have seen, there are a number of levels of cache present in our system. Say for example, if you have 5 levels of cache, so level 1 and 2 may be present in your CPU registers itself. So level 3 and level 4 may be used as separate chip devices, and or sometimes they may also be present in main memory itself as a part, in which that part of memory location will be considered as the cache memory. So when an instruction needs to be executed in CPU, that instruction is brought from main memory to cache memory and from there to the registers. So when it is brought from main memory to cache memory, this instruction is copied to all the 5 levels of cache. So whatever the number of levels of cache you have in your system, so this instruction is copied to all the levels of cache, so that when a process wants to change the data present in the shared memory, the data should be changed in all the levels of cache, which is not happening. So that's why these multiple copies of data cannot be changed at a time when a shared memory segment data is changed. So such a drawback is given for the shared memory model. And whatever the data is shared by these two processes, the communication between these two processes is not handled by the kernel. Okay, and the process are also responsible for ensuring that they are not writing to the same memory location simultaneously. Both the process, even if they are using the shared memory segment, both the process are not allowed to write into the same memory location at the same time. So for this, in order to control these two processes and avoid them writing into the shared memory At a time, we have the concept of process synchronization, which we'll be seeing in the next topics. And as an example of this shared memory model, let us consider a producer-consumer problem as an example. So now, what is this producer-consumer problem? Say for example, we have two processes in which one process will produce some item or one process will produce some data, and this data which is produced by the first process will be consumed by the or will be used by the other process. So the process which is going to give the data or produce an item is called a producer process, and the other process which is going to consume the data given by the producer is known as the consumer process. Okay, so in this case, if you consider some of the examples for producer-consumer process, say for example, when you write a program, let us think you are writing an assembly language program. So when you write an assembly language program, this assembly language program should be converted into machine code. So this machine code conversion can be done by the assembler. So when you try to convert this assembly language program, the assembler will generate different object files. Okay, so for one, if you try to compile or if you try to assemble one program, one assembler program, if you try to convert it to the machine code, the assembler will generate many number of object files. Say for example, if you are including some files into your program, all the object codes related to that files are also generated by the assembler. So once if you compile or if you send your assembly program to assembler, you will get the object code for your source file, the program which you have written, and the object code for the whatever the files you are including in your program, say for example a header file. So all these object files. Now here, if you consider assembler is producing number of object files. Here the items can be considered as the object files and the assembler can be considered as the producer. Okay, whereas these object files produced by the assembler are taken by the loader and linker. So the linker will take all these different files, combine it to a single file and produce an executable file. So here the linker will act as a consumer process. Okay, so the consumer process is a process which consumes all the data and it makes uses it for the execution. So here the loader and linker can be considered as the consumer process. Okay, it also provides a paradigm, it also provides a mechanism for the client-server architecture or client-server paradigm or client-server communication. Okay, so in general, a client is the one who will request something from the internet, say for example from the server. So say for example, if you are trying to search a word in your Google search, so you will be getting some websites into your browser. So in this case, the client or the person who is trying to get the information will be considered as the consumer, whereas the information that is displayed in your web browser is sent from the server. So from server you are getting some information. So the server is producing some information which is sent to the client. So in that case, the server can be acted as a producer and the client will be acting as the consumer process, which will consume the data given by the server. And then one solution to this producer-consumer, how these two processes will communicate with each other, how the consumer process will know that this is the exact data produced by the producer process. So one solution for this problem is the shared memory model. So here, in order to store the common variables or in order to store the items or the data produced by the producer process, the operating system will make use of the shared memory, and this shared memory can be considered as a buffer. So buffer here in the sense, you can consider the buffer as an array. So array is a collection of, is used to store the collection of elements, right? So here we consider an array, and that array in order to store the items produced by the producer, and that array can be considered as that array is called as a buffer. Okay, so the producer, whatever the item produced by the producer is placed into the buffer. When the consumer wants to take the item produced by the producer process, then it will access the buffer and consume the particular item. Okay, so the three conditions that should be kept in mind when implementing this producer consumer problem is, first thing is, the producer will only produce the data when there is a space in order to store that item in the buffer. If the buffer is completely full, the producer should not produce an item. And the second case is, the consumer will consume the data only when there is data present in the buffer. If the buffer is completely empty, the consumer process should not consume the data from the buffer. Okay, and the third condition we have is, both the producer and consumer process should not access the buffer at the same time. So this third condition can be achieved with the process synchronization, which we will be seeing in the next topics. Now the whole concept can be viewed in this diagram. See, if you observe here, the producer process will send its data to the buffer. So from that point, say for example, here we are considering the buffer as a circular cube, and whenever this producer produces an item, the item is placed in one of the location of the buffer. So wherever the item is placed by the producer, that item is consumed by the consumer process. So how these both the process will know where the item is placed by how the consumer will know where the item is placed by the producer process. For this, we will maintain two variables or two pointers called in and out. So if you observe the arrow marks on the producer process side, so the arrow mark will indicate the direction in which the producer process is going to place its items, and the arrow mark, the black color arrow mark around the circular cube on the right hand side, on the consumer process side, will indicate the direction how the consumer process will consume an item produced by the producer. Okay, so with this concept, we'll see how this producer and consumer process will be actually implemented. So before going to the implementation, let us see what are the types of buffers used in order to store this information. So this circular buffer which we have seen can be of two types. Okay, so the buffer we are using can be of two types. So one is unbounded buffer and the other is bounded buffer. So unbounded buffer will have no size limit, will have no maximum size limit, whereas bounded buffer will have a maximum size limit. Say for example 10. If you are giving the buffer size as 10, the producer process can store up to 10 items in the buffer. If the buffer is if the buffer is completely filled with 10 items, then the consumer cannot consume an item, the producer cannot produce an item into the buffer. Okay, so that is about the two types of buffers we are going to use. And coming to the implementation, first we'll see what are the elements that are stored in the shared memory.
So now coming to the implementation, let us see first what actually the variables these both producer and consumer process are going to share in their shared memory segment. So if you consider the producer process as a process which is going to produce, say for example, laptops. So in these laptops we have number of details like name of the laptop, hard disk size of the laptop, and RAM size of the laptop. So all these properties together can be called as an item which is produced by the producer process. So you can think here the producer as an organization which is going to produce a laptop and which consists of the details like name, hard disk size and RAM size. So now this item which is consisting of name, hard disk size and RAM can together be created as a single type in C language using structures. So let us see how this item can be built in C using the structures. So here we are using the structure type, and then this structure will include all the details like name of the laptop. So to store the name of the laptop, here I am taking a variable called name, which is an array which can store 20 characters in it, and then I have two integer variables in order to store the size of the hard disk and the RAM. So all these variables together can be considered as one data type using this structure, and this structure is named as item. So now when the producer process is producing an item, that item should be placed in the buffer. So here the buffer is nothing but an array. So in order to declare an array, we need to provide the data type of that buffer. Here if you see, the item is the type or data type of the item produced by the producer. Buffer is the name of the array, and here the buffer size is a macro which defines the maximum size of the buffer. And I have also taken two variables in and out, which will point in case of producer. The variable in is a pointer which points to the next empty location in which the producer has to place its item. Okay, whereas out is the next full location or the next item's location in which the consumer has to consume the item produced by the producer. Now if you see, the overall code of present in your shared memory can be like this. So a structure which consists of all the items of the all the details of the item, and a buffer which consists of the size of the buffer, which is an array consisting of the size of the buffer. So here the buffer size is defined as 10, and in and out are the pointers used for producer and consumer process. So here the condition we have seen three conditions previously for producer and consumer problem. So condition 1 is the producer have to produce only if the buffer is not full. Okay, so if the buffer is full, then the condition would be like this: in plus 1, that is the pointer or where the pointer where the location where the producer want to produce an item, that current location plus 1 divided by the buffer size. If it is equal to the out pointer's location, then you can say the buffer is full. And the second condition is the consumer should not consume an item if the buffer is empty. And the condition for an empty buffer is the location where the in pointer is pointing out should be equal to the pointer out, which is indicated or which is used by the consumer process. So here, if in pointer, the location where the in pointer is pointing, if it is equal to the out pointer, then we can say that the buffer is empty. So these are the variables which are shared by both the producer and consumer process. Now let us see the code for your producer process. here, in order to store the item produced by the producer process, I have taken a variable called next produced. So the data type of this item is the item data type, which is a structure we have defined in the shared memory. And this producer process, the task of this producer process is to always produce some item. So I have taken a true loop, that is a infinite loop, which will keep on executing in order to produce an item until an erroneous or stop condition has been occurred. Okay, so here, in order to continuously produce items, I am taking a while loop. So while true, you need to produce an item. So before producing an item, if the buffer is if the buffer is not empty, that is, if the buffer is full, we have seen the buffer full condition is in plus 1 mod buffer size equal to out. So if the buffer is full, your producer process should not produce anything. In that case, so while buffer is full, your producer process will not do anything. If the buffer is not full, then the buffer is an array. So here, array of, initially we have taken the in value as 0 in the shared memory. If you observe here, the in value is 0. So the first item produced by this producer is stored in buffer of 0. So that buffer of 0 will store the item produced. So then you have to, the in pointer will point to the next empty location. For that, in order to point to the next empty location, we have taken in plus 1. So since this is an, here for simplicity we have declared this in as a normal integer variable. Okay, so here in order to increment the value of this index in, we can simply write in plus 1, but whereas here we are considering this buffer, this array, as a circular queue. So in case of circular queue, when the last location is, and see, say for example, if this is the circular queue, okay, this is position 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. If these are the 10 items to be placed in this buffer, if this is the 0th location and this is the 9th location. So say for example, if your pointer in is at last location, okay, so if the pointer is at last location, location number 9, so next increment, if you simply write in plus plus, so 9 plus 1 you will be getting 10, where the 10th location is not present in our circular queue, that is the buffer. So for this, in order to get the again starting location, we are writing the condition in plus 1 mod buffer size. See, if the in value is 9 plus 1 mod, the buffer size here we have defined as 10. So 9 plus 1, 10 mod 10 will give you the result 0, which is the next location of your buffer. So for this purpose, we have, instead of writing simply in plus plus or in plus 1, we have divided it with the buffer size. So this is the code for your producer. So once the in pointer is pointing to the next location, now the buffer will produce an item into this next location if this location is empty. If this is full, the condition in plus 1 mod buffer size will be equal to out and your producer will not produce an item. So this is the producer code. Whereas coming to the consumer code, here you need to consume an item. The consumer process need to consume an item from the buffer. So in order to consume an item from the buffer, I have taken a variable to store the consumed item. So next consumed and the data type is item. So here again this consumer process also should keep on consuming the data or the items produced by the producer. So the only condition when this consumer process should not consume is when the buffer is empty, and the condition for buffer empty is in is equal to out. So while in is equal to out, your consumer process will not consume anything. If this condition is not satisfied, then the next consumed is taken from the buffer at position where the pointer out is pointing to. So this is placed in the variable next consumed, and it is used for further processing. So after consuming an item from this location, you need to increment the value out for pointing to the next item in order to consume. So for that we have taken this condition, same as we have seen previous producer process how to increment the in pointer. In the same way we are incrementing the out pointer here in order to point to the next location to consume an item. Okay, so likewise the consumer process will consume all the items produced by the producer, and whenever the buffer is empty, the consumer process will not consume anything.
Using the shared memory, using the variables present in your shared memory, we have implemented the producer and consumer process. And the second model we have for inter-process communication is the message passing model. So if you observe, in shared memory model, the operating system will be active until only the shared memory has been established between the two processes. Whereas in message passing model, each and every action in order to send a message from one process to other will involve the execution of an system called by the operating system. So the kernel will always be active until the communication between the two processes is completed. Okay, so here if you observe the diagram, the process A and process B are the two processes which wanted to communicate with each other. So when they wanted to communicate with each other, they will be allocated some space in order to store their messages from both the process. Okay, so these message passing model will be implemented by exchanging the messages between the two processes. Okay, here you will not have the common shared memory between the two processes. The kernel will store, say for example, now process A wants to send a message to process B. Now the process A will send the message to the port, or it is also called as a mailbox. A common mailbox is shared between the two processes, and this mailbox is present with your kernel. So when process A wants to send a message, the message is sent to the mailbox created for communication of these two processes. Okay, that mailbox is present with your kernel. So once a message is sent to your mailbox, the kernel will take care about the messages sent by a process. So whichever the process want to receive that message will access that same mailbox present in the kernel. Okay, and this message passing model is mainly designed only for small data transmissions. Okay, small data in order to provide communication for smaller amounts of data. Okay, and the message passing models are completely implemented using the system calls. If you want to send a message, you need to execute a system call. If the receiver process wants to receive a message, the receiver process wants to has to execute a system call by the operating system. And this mechanism will allow the process to communicate with each other, as well as it also allows the process to synchronize with each other, that is one after the other can access the mailbox. Okay, and this is particularly useful in distributed environment. What is this distributed environment again? So in a network, when there are different systems connected with each other, you can share the resources of other computers connected in that network. Like the resources, in the sense you can share the memory of other computer into your computer and use the whole memory. Say for example, if you have only 4 GB of RAM in your computer, and the other computer connected to your distributed network will have some 4 GB of RAM. So you can share some amount of memory from other system and make use of it in order to execute your process. So in order to implement such environment, in order to implement such network, we can make use of the message passing model. Madam, please. So that is about the distributed environment. And the best example for this message passing model is your internet chat program. Either it may be WhatsApp or through Gmail Hangouts or through Facebook chat. So whatever it is, all these make use of this message passing model in order to send and receive messages through your friends. Okay, the message passing model will make use of two system calls in order to send and receive messages by the user. One is the send system call and the other is the receive system call. And whenever a message is sent by a process, so whenever we want to send a message to other process, the messages can be of two types. One is a fixed size message and the other is the variable sized message. A fixed sized message will have the higher limit of total number of characters that can be sent by the process. Say for example, if you consider a normal text message sent through your SIM card without using any applications, so you have a limit of 160 characters, right? Whereas in WhatsApp or through some social media application, you can send the text without any limit of number of characters. Okay, so here the text message or the normal text message which you are sending from SIM card to other SIM card can be considered as a fixed sized message. Only in a single message, only 160 characters can be sent to the other user. So such messages are called fixed sized messages, and whereas variable sized messages are those which will not have any size limit. Okay, in case of fixed messages, user may feel difficult to use such type of environment, whereas the system level implementation, the background program which is the program developed for such fixed sized messages will be easy to implement. Whereas in variable sized messages, the user feels easy to use it, whereas the implementation will be a little complex. Okay, so now when two processes wanted to communicate with each other, first thing we need is a communication link must be established between the two processes. Okay, so the link may be the physical implementation or the logical implementation. So in case of physical implementation, your link may be a shared memory or a bus. So a bus is a cable which is used to transfer data from one device to or one part or one process to other process. Okay, or you may need to communicate between two different computers in different networks. Okay, then you need to provide some internet connection. So here this connection can be considered as a communication link. And in case of logical implementation of this link, there are different methods or different methods in order to implement or in order to send and receive the messages from each process. So we have The three methods are direct and indirect communication, synchronous and asynchronous communication, as well as automatic and explicit buffering. So automatic and explicit buffering. So now first let us see the direct communication. So either of the case, either in direct or indirect communication, the sending and receiving process must mention their names in the system call that is being used by the operating system. Okay. So when these two processes wanted to communicate with each other, they has to provide their name. Okay. So see here on the screen, you can observe in order to send a message, if there are two processes P and Q, okay, now if Q want to send a message to process P, then Q will execute a system call called send. So in order to send a message from Q to P, Q will execute a system call called send and with parameters. First, P is the name of the process with which the message has to be passed and the actual message that has to be passed to the process P. So send will have the parameters. First is the name of the process to which the message has to be sent, as well as the actual message that has to be passed to process P. Now, at the receiving process side, if the process P wants to receive the message sent by process Q, then this process have to execute a system call receive system call with parameters as the first parameter here for the receive system call is the name of the process which is sending the message and that actual message. Okay. So the communication link established between these two processes P and Q can have some properties. So the link is established in direct communication. The link is established automatically. So whenever two processes want to communicate with each other, a common mailbox will be created, and so the communication link between these two processes is established automatically through this mailbox. Okay, and once the link is established, the link will be associated with only two processes, sending and receiving process. Okay, and between each pair of process there exists only one link. So if PQ wants to communicate, only one link will be established for their communication. So if you see the above seen protocols, like the above seen system calls, the send and receive system calls use their names as parameters. This kind of execution of system call is called symmetry in addressing. Symmetry in addressing in the sense the sender will mention the receiver's name and the receiver will also mention the sender's name. Okay. If we have one more case called asymmetry in addressing. In this case, the sender will attach the name of the receiver, whereas the receiver need not attach the name of the sender. Okay. So if you observe the receive system call here, the receive system call, instead of having the name of the process, here it is having the ID as an identifier. This identifier which will accept all the messages sent by different processes. So asymmetry in process in the sense the receiver process, the asymmetry in addressing in the sense the receiver process is capable of accepting all the messages sent by different senders, whereas in symmetry in addressing a process cannot accept or cannot receive a message from other process. The communication link established between two processes, if a communication link is established, only that process can send a message to this receiver. So the disadvantages of this type of approach, this direct communication, is limited modularity. You cannot divide more number of modules of your complex program. Okay, so whenever more number of modules are divided, each and every module's identifiers or each and every module names must be loaded into the system calls every time. Okay, and indirect communication. So in indirect communication, the send and receive system calls will not make the send and receive system calls will not make use of the name of the process. Instead of name of the process, it will use the name of the mailbox created commonly for communication between these two processes. This mailbox is also called as a port. Okay, so a port is a number which is above 1024 in your system. See, say for example, if you are logging into your system for online exams, you can observe after the IP address colon 8080 something. So that 8080 is the port number in which the data related to your application can be received by your system. Okay, so through this port number, the data will be received by your system and placed in the corresponding application which is displayed on the monitor. Okay, and each mailbox has a unique identification. Okay, each and every mailbox will have an identification number, and two processes can communicate with each other in this indirect communication only if they have a common mailbox established. If there is no mailbox established, then there will not be any communication between these two processes. Okay, and here in indirect communication, if you observe, the system calls will look like this. So the send, if you want to send a message to a receiver, the sender process will execute the send system call with mailbox name as parameter as well as followed by the message as the second parameter, actual message what it want to send to the receiver. And this message, when it is executing the send system call, the actual message is sent to the mailbox given for this process. So now when the receiver process wanted to access this data, the receive system call is executed by the receiver process, and the receiver process is going to access the mailbox given for this process. So in this scheme, the communication in indirect communication, the communication link between these two processes will have the following, will have the properties like: the link is established between a pair of processes only if both members of the pair have a shared memory mailbox. So we have discussed, if there is no shared mailbox, then there is no communication between these two processes. And a link may be associated with more than two processes. Whereas in direct communication, a link can have only exactly two processes, a sender and a receiver. Whereas in indirect communication, a link may be associated with number of processes. That's why here a receiver can receive message from different senders. Okay. So between each pair of communicating process, a number of different links may exist. Okay. Whereas in direct communication, between each pair, only one single communication link can be established. Whereas between in indirect, there are number of communication links. And as an example, if you consider three processes P1, P2 and P3, let us assume all these three processes are sharing the same mailbox. Say for example, mailbox A. Let us think the name of the mailbox as A. Now, if you think P1 is a process which is going to send the messages to two processes, P2 and P3. Now P2 and P3 are the receiver process, so they have to execute the receive system call, whereas P1 is a sender process, so it will execute the send system call. So now if the P1 process sends a message to mailbox A, that message can be accessed by P2 or P3. How the operating system will decide which process, either P2 or P3, have to receive the message sent by the process P1. So in order to decide to which process the message has to be received, the first is we need to allow the link to be associated with two processes at most, because we have two receiver process P2 and P3. So we can associate the link to make both the process to receive the message simultaneously. And the second case is you can allow at most one process at a time to execute a receive operation. That is, once after P1 has sent a message, at a time only one process can execute a receive system call. That is, one process can receive the message at a time. Okay, so both the process here in this second case, both the process cannot receive the message at a time. And third condition here is you can allow the operating system itself to randomly choose one of the process, either P2 or P3. Since we have two available receiver process, you can allow the operating system to select either of these two process. Either P2 can execute the receive system call or P3 can execute the receive system call, but not the both. So in third case, the operating system will select the process to receive a message. And this mailbox can be owned. The owner of the mailbox can be of two types. So the owner of the mailbox can be a process, or the mailbox, the owner of this mailbox can be a operating system. See, say for example, if you consider a Gmail, you are the owner of your Gmail account, right? Without having a ID or without having a Gmail ID, you cannot view the email, you cannot view the inbox of your Gmail, right? So in the same way, the mailbox should have some owner. So this owner may be a process. Say for example, the sender process. The sender process may be the owner of the mailbox or the operating system. If the process is the owner of your mailbox, the process can only receive messages from the other senders, but it cannot be able to send the messages through this mailbox. If the operating system is the owner of this mailbox, then the operating system will provide the process in order to send and receive the messages. That is, it can provide mechanism to create a new mailbox. It can provide a mechanism to send and receive messages, or it can allow a process to delete a mailbox. Okay. But overall, if the process is the owner, then whenever the process exits from the execution, the mailbox will also disappear from the memory. And then that is about the direct and indirect communication. And then we have synchronization. So synchronization here in the sense, both the process cannot access the mailbox simultaneously. We have the synchronization. So we have discussed the 3 points of producer-consumer problem. One is the producer will not produce if the buffer is full. Second is the consumer will not consume if the buffer is empty. And the third is both the process will not exchange information simultaneously. That third point can be achieved with this synchronization. So synchronization in the sense, when one process is accessing the shared memory or when one process is accessing the mailbox, the other process will not be allowed to access the same memory. Okay. So for this, your operating system will provide synchronization or by passing messages with two possibilities, either blocking or non-blocking. So if it is a blocking message, then it can be called as a synchronous message passing. If it is a non-blocking message passing, then it can be considered as a asynchronous message passing. So here there are 4 methods in order to block each process. First is the blocking send. So in blocking send, when the sender process will be stopped until the message is received either by the mailbox or by the receiver. So once a process sends a message, that message will be sent to the mailbox first. From there, whenever the receiving process will execute the receive system call, this message will be passed to the receive system call. So here, whenever the process is in blocking send mechanism, whenever the process sends a message the process will wait until the message is received by the mailbox or by the receiver. Then only this process will start sending the next message. Whereas in non-blocking send, once the message leaves the process will continue sending with the next message. It is not bothered whether the message is received by the mailbox or it is received by the receiver. Okay, so in non-blocking mechanism, as soon as the message is sent out from the process will start creating the second message and it will try to send the message out of the process. And next we have is the blocking receive. So blocking receive. In this mechanism, the receiver will be blocked until the message is available. If the mailbox is empty, the receiver will not be allowed to execute the receive system call. Whenever the sender process sends a message to the mailbox, then only the receiver will be unblocked to receive that message from the mailbox. Okay. Whereas the last thing we have is the non-blocking receive. Here, whatever the case, whatever the data present in the mailbox can be accessed by the receiver. If there is no data present in the mailbox, then also the receiver process will be executing the receive system call in order to get the data in the mailbox. If there is no data present in the mailbox, a null character will be received by the receiving process. So the different combinations of these four concepts can have the blocking send and non-blocking send will be executed by the sending process, and the blocking and non-blocking receive will be executed by the receiving process. So sender process will execute send system call, whereas the receiver process will execute the receive system call. So this send and receive system calls, the number of combinations of send and receive system calls may be possible in this model. So you can have a blocking send and an unblocking receive, a blocking send and blocking receive, and unblocking send, blocking receive, unblocking send and unblocking receive. Either of the combinations is possible with the send and receive system calls. The solution of your producer and consumer problem will become trivial in the sense less importance. Your producer and consumer problem will have less importance if it implements this blocking send and blocking receive combination. Because here with blocking send and blocking receive combination, you are getting the process synchronization so that the producer and consumer will not try to access the same memory or access the same mailbox at a time, and with which fulfills our third condition in our producer-consumer problem. Okay, so the producer will invoke a blocking send and waits until the message is delivered to the receiver, and the receiver or the mailbox. The same way, when the consumer invokes a receive system call, it is blocked until a message is received by the mailbox. Okay. The last concept we have in message passing model is the buffering. So in order to use the type of memory for a mailbox, here we can make use of different types of buffers. So these buffers can be implemented in three ways. One is zero capacity buffer. Zero capacity buffer in the sense, as soon as the producer process produces an item, that item will be directly received by the consumer process, because there is no space for storing that particular item in the mailbox or in the shared memory. Okay, and second we have is the bounded capacity. So bounded capacity in the sense, the queue or the buffer will have the maximum limit or the maximum size. Say if you give the size of the buffer as n, only n items can be placed in the buffer, whereas the remaining cannot be placed in the buffer. And then you have the third type of third type you have is the unbounded capacity buffer. Unbounded in the sense there is no size limit for your buffer. Any number of items can be stored in your buffer, so that the producer will not have to wait until the buffer becomes empty, because it is capable of adding any number of items into the buffer. Thank you for watching this video. Next video we'll be seeing about the communication between the client and server systems using the inter-process communication. Thank you for watching.